Thank you. Good afternoon. This session is about the future, and I just want to say that what I'm going to show you has not been used on any patients yet. As a matter of fact, we just installed the latest version of the software on Sunday, and most of what is here came in today and yesterday. I do want to echo the theme that pressure leads to productivity, because when Moritz and Klaus asked me to give this talk, I had absolutely no content on mixed reality for periacetabular osteotomy, and the pressure really led to a little bit of productivity. I'd like to acknowledge a lot of people, some in the room, some not, but our previous fellows, Moritz and Simon, are here. Michael Millis is here. Pat Lane is here. And in particular, I'd like to acknowledge a couple of people. Maurice Mueller, many of you didn't know Maurice, but I think we're all here because of him. He really brought hip surgery to the forefront in burn and was really on par with John Charley in terms of what he achieved in his career. He funded a lot of research, created a research foundation here, funded the training of a lot of us, both on the research side and clinically, and that led to a lot more work in the hip, including Reinhold's tenure, and now Klaus's tenure as chairman in burn. An amazing man. I'd also like to acknowledge Jens Koval. He and I, Jens originally, we met when he was working at the Maurice Mueller Institute, and we have been working together continuously for the last 15 years in a bunch of areas, including surgical navigation, smart tool navigation, surgery planning, and as you'll see, mixed reality guidance, and Jens is here as well. So periacetabular osteotomy, as you know, it's a very anatomical operation, pathomechanics, and it's something that you can simulate, it's something that you can accomplish, it's something that's perfect for patient-specific mixed reality guidance. So years ago, everyone got involved in, and we did prediction of joint contact pressures before and after periacetabular osteotomy in the mid-1990s. And that's all great to simulate what it is that you want to achieve, but then the question is, how do you get to that goal intraoperatively? And there are a number of ways. Chris Peters talked about fluoroscopy and quantitative fluoroscopic measurements in surgery to elevate the goals of surgery to accomplish them. Surgical navigation has been used a little bit, but not routinely. And the topic of this is mixed reality guidance. So basics of mixed reality guidance, and in this way I'm talking about patient-specific mixed reality guidance where we know what the person looks like and we're projecting that information inside their body. So you plan what you want to display in advance, generally, and then you load those 3D files onto a mixed reality device. You put image trackers into the field, and you put on a head-mounted device that can use image recognition and tracking. And then once your device recognizes that image, you give it the mathematics to project the information inside the body. And so you can project anything you want. So when you talk about 3D printing, this is essentially instant 3D printing for your brain. You don't actually have to physically print anything. And of course, you can do this overnight or even same day. So in terms of tracking, this is the HoloLens 2 from Microsoft. It has 4 cameras on the forehead. They can anchor and track using image recognition and tracking methodology, which we leverage heavily. And this replaces all the other tracking methodologies, infrared stereoscopic tracking, which is the most common one, or inertial tracking. So here we are. What would you do with mixed reality for periacetabular osteotomy? Well, we make bone cuts to separate the socket from the rest of the pelvis, obviously. Those can all be planned. These are separate cut planes. They tend to be flat planes the way we do PAO, and so they can be planned as separate cut planes. And then you can separate the socket from the rest of the pelvis just like you do in the real surgery. And any of these at any point can be exported as a three-dimensional model that you can display inside the patient if you want to. So now you've cut that, you've created a separate fragment. Then you can move the fragment any way you want. Of course, we have coordinate systems here. We can measure the 6 degrees of freedom motion of the one fragment relative to the other and display it on your forehead if we want to. And then we create a final rendering of where we want that acetabular component to be and then export a three-dimensional model of that. So here's just an example in a planning module of the retroacetabular cut plane. You can move this around freely. These planes are bigger than the actual cut planes, but when they intersect, they do the calculations at plane intersections so that the size of the plane itself doesn't matter. So here are all the cuts made, you can see. And once you have your cut planes in the right place, you can activate the separate fragment. You can start moving it around. You can remove the cut planes from your view if you want. And you can export all of these in a sequence. So this was just from today. That's a bone model with a tracker on it. Now that's the augmented reality display over the bone model. That's the pubic cut that's being displayed. Of course, this is live, and it would be buried inside the person's body, so you would be seeing through the skin as this is happening. Supraacetabular cut, retroacetabular cut, and then the ischial cut, which we usually do first, is displayed there. And now these are all holograms being displayed through the lens as it's anchored onto this bone model, which is exactly the same as doing it inside a patient. Now we have another hologram, which is the separate fragment, and then that's the repositioned acetabular component. And if anybody wants to see this, we have bone models here, we have lenses here. It takes 5 minutes. So. And this is what we were doing. This is quite different. I mean, this is 1995. We were using an articulated digitizer, putting screws in the acetabular fragment, digitizing it before and after, doing calculations on rotations and calculating joint contact pressures a few decades ago. And this is essentially a very modern version of the same thing, knowing where to make the cuts, knowing where to put it, and accomplishing it. So in summary, we usually just track the pelvis and then display everything else relative to it. You can track other objects too. You could track osteotomes or track the acetabular fragment being repositioned. You just have to decide what you want to do. And then you anchor to the patient and you project it all. So I do think that PAO traditionally has been heavily fluoroscopic based, which is fine. But this is a very objective, quantifiable, displayable, intuitive way to evolve this operation, and it's possible even to decrease the use of fluoroscopy and increase the accuracy quite a bit. Thanks very much.